Okay guys, in this video, in this chapter, we're going to talk about area of quadrilaterals. Now, area of quadrilaterals is sort of the very foundation of all area and all volume later on, all surface area. This is the very foundation. From here, we can go to triangles, we can go to polygons from triangles. So this is really the beginning of all of where area and then later on surface area and volume come from. So if you understand this, or you have to have a good understanding of area of quadrilaterals before you can have a deep understanding of triangles, polygons, cubes, cones, whatever, right? So two-dimensional, three-dimensional, it all starts here with quadrilaterals. So the base, the very foundation, the core of area is a square, okay? A 1 by 1 square, all right? And so the area of this square, is going to equal 1 unit squared. Now, before we talk about, before we get into all this talking about formulas and stuff, I want to note that this sometimes is confusing to students. I will say that it should not be, in this case it doesn't matter if you do 1 squared, because 1 squared is still 1. But sometimes people like to do, they like to square the actual number, which in the case of a square is okay, but and we'll look at further examples of why that's not a good idea. So really the unit is squared, and the reason that is, for example, if you have 1 centimeter times 1 centimeter, well, 1 times 1 is 1, and centimeter times centimeter is centimeter times centimeter, so centimeter squared. So it's 1 unit times 1 unit. 1 times 1 is 1. Unit times unit is unit squared. So it acts exactly like a variable x or something almost. So this is sort of the very foundation. Now from here, we can go on to a rectangle. So from square we go into a rectangle. So let's say we need to find an area of this rectangle. We have 1 by 3. Okay, so 1 by 3, well, what we can do is, again, we go back to our base. We go back to the square. And we can split this up into 1, 2, 3, right? Now we know that the area of this is 1, the area of this is 1, and the area of this is 1. Okay, so we have a 1, we have 1, 1, 1, right? So 1 by 1, 1 by 1, and 1 by 1. So the area of this is going to equal 3 units squared. Okay. Let me draw another, slightly more complex example, although it won't be to scale. Let me draw this example, and let's just say this is, let's say, 5 by 3. Okay, so now from any rectangle, you're going to do the same theoretical idea. 5 by 3, what we're going to do is we're going to split this up into 3 here. Okay, so 1, 2, 3. Okay, and we're going to break this up into 5. So 1, 2, 3, 4. And now, even though my drawing is not perfect, these should all be cubes, 1 by 1 cubes. So how many cubes do we have? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9. Anyway, we have 15, right? We have 5 plus 5 plus 5, or 3 plus 3 plus 3 plus 3 plus 3. Okay, so this foundation is, or this idea is going to be the very foundation of all rectangles, which will be the foundation of all quadrilaterals. So hopefully, the area of this then would be 15 units squared. Okay. So sometimes when people deal with this squared, let me get back to that, they do 3 times 5, which is 15, and then they want to do 15 squared. Okay, and 15 squared is 225. So the area of this, there's obviously not 225 unit boxes here. Okay, so there's only 15, so it's actually the units that are getting squared. So hopefully I think most people have a fairly good idea about this. What gets a little confusing is when we get into other types of a bit more complex quadrilaterals. Now, here's what I'm going to tell you a lot. You're going to hear me say this so many times. In geometry, in area, volume, surface area. Okay, what you have to do is you have to, like, for example, right now we don't know how to find these, okay, because we haven't covered it. All right, now in geometry you have to take what you take what you know and use that on something you don't know. Okay, so we just did this right here. Okay, so I didn't know how to find the area of a rectangle, but I thought, oh, I can make a rectangle into some squares, and I know how to find a square. So by that same logic, you have to take something that you know and apply it to something you don't know, and then see sort of where that gets you. So let me, before we move on to here, let me write down the area. The area of a square, so a square, let's see here, area of a square is going to equal, you can just say side squared. Okay, and the area of a rectangle, so this is a square, and this is a rectangle. So area is going to equal, it's just going to be length times width. Okay, so length times width. Or you can say base times height. Either one is okay. So these are sort of our foundations. Now let's move on to some more complex parallelogram, trapezoid, round by kites. Okay, some more complex quadrilaterals. All right, so now what we have here, parallelogram. So parallelogram, maybe we don't know how to find that. But we can use a rectangle or a square, and we can try to find it. So let's say we have, this is the base. Okay, so here we have the base. All right, now notice that we also have a base in a rectangle. Okay, we have a base in a rectangle. So if I can have a base in a rectangle, then if I could just get a height of the rectangle, then we would be, we could find the area. So here's the height. All right, so there is the height of that rectangle. Now, if I want to find that white thing is going to be h. Okay, so that white line there is h. Now, so in this picture, in this picture, let me use a different marker here. In this picture, b times h. All right, what does that geometrically represent? So we have an algebraic expression here. What does that geometrically represent? All right, well, it looks like, going back to what we know about rectangles, geometrically, that's going to be a rectangle. Okay, so what does this line represent? We draw in the height here. Okay, and this base times height is going to equal the area of this rectangle. Okay. So the question is, if we can take this triangle, and if that fits right into here, then we can use this equation. So let's see here. This is the height. All right. Now, I guess the question is, are these two triangles congruent? If they're congruent, then we can just slide that over here. So I know this is a right angle. Okay. We know that these are right angles as well. Okay. All right, because that's the definition of a rectangle and altitudes, right? So what we have here then is that these two lines are parallel. These two lines are parallel. That means that these two lines, this white line here and this white line, must be congruent. Okay. So those are congruent. And we also know that we have, let's see here, these lines are going to be parallel, right? These lines are parallel. So we know that these two angles, let's see here, these two angles, well actually, and these two angles are going to be congruent. So these two triangles are congruent. And so we can actually use this formula, base times height of any parallelogram. So area, let me write this down, area equals base times height. Now you have to recall, what is the base, what is the height, okay? So we're not talking about this sort of slant height, we're talking about a perpendicular line to the base, okay? So this is the area of any parallelogram. All right. Trapezoid. Now remember when we talked about trapezoids, we talked about the mid-segment theorem, okay? And the mid-segment was basically this line. Okay, it was a line that went from here to here. Okay, and basically it cut these lines in half. It went through the midpoint of these two lines. Now, again, we know that this is, we know by the trapezoid mid-segment theorem that this line equals 1/2. Okay, so this line equals, so 1/2 base 1 plus base 2. 1/2 base 1 plus base 2. So we know that from the triangle mid-segment, or sorry, trapezoid mid-segment theorem. Now, again, maybe we don't know how to find the area of a trapezoid, but we have to go back and use something that we know how to use. Okay, so let's say I multiplied this. I'm trying to see if I can put a rectangle in here that would sort of represent the shape and the exact area of this trapezoid. And I'm thinking if I could draw this in here, and if I could make this rectangle here, okay, I think then that could be, that could be, we could just take this part and put it into there, and then we would have this line times this height would do it for us. So let me check that. Well, we know that these two are vertical angles. Okay, so they're congruent. We know that two parallel lines cut by a transversal. We know that alternate interior angles are congruent. So by AA right triangle congruence, these two triangles are congruent. So in fact, if we do, this line is 1/2 B1 plus B2, so this is the, let me write this down, this is the mid-segment, and this is obviously the height, okay? And so we have that picture there. I think this is probably easiest for you to visualize, but yeah, this would be the formula. Sometimes it's written different ways, any mathematical equivalent. I know when I learned the trapezoid formula, the area, I think the first time in 6th grade is when I learned this, because I still remember my teacher, and she would always sing this crazy song. But she would always sing base 1 plus base 2 divided by 2 times the height, and she made us sing that a lot. I still remember it. And so any mathematical equivalent of this, b1 plus b2 times h over 2, those would all be okay. But basically, I think this representation helps us understand algebraically what's happening geometrically. So let me look at another example here, because this one is not the only type of trapezoid we see. So I want to come up here and quickly draw another trapezoid and see would this same rule apply. Okay, so we have this base 1, base 2, trapezoid. We know that means the definition of a trapezoid is that these two bases are parallel. Okay, so now using the same logic, I want to find the mid-segment. Let me use a different color here. Okay, so I want to find the mid-segment here. All right, and the mid-segment says that it's going to divide these in half. So that mid-segment is base 1 plus base 2 times 1/2. All right, and again, this all stems from the trapezoid mid-segment theorem. Okay, now if I could find the height of this, the height here, it looks like, again, we could maybe take both of these smaller triangles and spin them up to the side. And again, by the same logic that I used here to show that these two triangles are congruent, you can use the same thing here. It's going to be by AA. So these two triangles are congruent by AA, and you can actually fit both of those nicely into this trapezoid. So for all trapezoids, this is the equation, and that's why. 1/2 base 1 plus base 2 times the height. Okay, finally, let's get to rhombi and kites. Okay, rhombi and kites, you know that they share a special, if you recall the properties of rhombi and kites, you know that these share a special property in them, and maybe if you remember, which one they share, that will hint you, that'll give you a hint as to what the formula is. So, if you don't remember, I'll just sort of give you the answer. But rhombi and kites share the property that their diagonals, okay, their diagonals always, always, always intersect in right angles. Okay, diagonals always, always, always intersect in right angles. Sorry, diagonals of kites and diagonals of rhombi. Okay, so always, always, always intersect in right angles. Now, I hope you see where I'm going with this. Again, we have to take something that we know to use to find something that we don't know. So again, I'm going to use a rectangle here. Okay, if we make a rectangle, okay, something like that. All right, and I think you can see pretty well that, you know, basically, if you take this rectangle, okay, this big rectangle, and if you, it looks like half of that rectangle space is taken up. So if you can take the big rectangle and then take half of that, then that'll be the area maybe. So let me see if that works here. How am I going to draw this here? Okay, it's going to be a little bit more difficult here. I've got to do something like this. I have to turn my head to make sure I'm drawing this correctly. Okay, and so I've drawn, this one is not as good, but I've drawn the same sort of thing happening here as well. And so let me just talk briefly, are these actually mathematically, are they congruent? How do we know they're congruent? Okay, well, we know that this is a right angle and this is a right angle, so all of these are right angles. I'll just focus on one of these sets of triangles, and we will just, you know, by the same logic, show that you know, these are that all of these are congruent. Okay, so how do we know then? Well, what I've done is basically, you know, we have two right angles, we have a shared side. So if I could show that for example, you know, these two sides are congruent, then we would be, or if I could show, let's see, I could use this angle here, right? So if I could do angle, side, angle, or angle, side, or sorry, angle, angle, side, angle, angle, side, so AAS, that's possible. So are these two congruent? Well, we know if this is 90 degrees and this is 90 degrees, then these two must be 90 degrees. Okay, that means it's a rectangle. Rectangles are parallelograms. So if these are parallelograms, then we know that these two angles are the same. So circle here, I'll put a dot there, and a dot here. Those two angles are the same. So we have AAS and AAS. Okay, so AAS shows that these are the same. That's going to work with all of these triangles, in fact. And so what you have to do is, what does this box represent? We've seen it geometrically, but what does that look like algebraically? Well, the area, this box, is going to be, it looks like this is one of the diagonals, this is another of the diagonals. So we don't have a base and a height, but instead we have D1 times D2, okay, equals D1 times D2, so that's diagonal 1 times diagonal 2 gives us this rectangle, and then times 1/2, half of that. Okay, so hopefully this gave you a decent idea of where, you know, if I just gave you this formula and said do 1,000 problems or something, or if I gave you this formula, certainly, I think many kids are just given this formula, they don't have any idea really where it comes from. But again, this is all the foundation of everything we're going to do with area, surface area, and volume. And so hopefully this gave you an idea. Maybe you've never seen where these things come from, and now you can say, oh wow, this, you know, I understand this. This isn't just random numbers. So hopefully this helped you out. In the next video, we're going to look at some examples and then go from there. Thanks for watching.